Now that we understand that batching production flow units can increase our capacity when setup times are present, we want to look at the trade-off between flow rate and inventory. Our learning objectives are to understand how to choose an optimal batch size for processes with setups, to explain the trade-off between flow rate and inventory in batch production, and to understand and discuss the impact of setups and batching in lean production. So looking at our propeller example, we have a capacity of 9 units per hour at assembly here. And at the machining step, however, we found out that the capacity depended on the batch size. And here we looked at the data. The larger the batch size, the larger the capacity. So what would we do? Let's pick a good batch size here at machining so that we're not limited. We're not limited by our setup times. How about a batch size of 10? Gives us a capacity of 9.68 units per hour. You can look at a graph here of the same information. So don't forget a batch size of 1. We had then a capacity of 7.5 units per hour. For 3, we had a batch size of 9 units per hour. And then for 10, you can see that we have a batch size of in this case, it was batch size over setup time, batch size times time per flow unit, batch size of 10, setup time is 2, plus 10 times 6. So we end up with 10 over 62, which is 0.1613 units per minute. And have this on the other slide. We end up with 9.68 units per hour with a batch size of 10. So you can see that here. 9.68 units per hour. Great. Let's look at our decision here. We have 9.68 units per hour here as our capacity. And everything should be fine, right? What's wrong here? The base and the propeller heads being produced in batches 10, but they can only be assembled with a rate of 9 units per hour at assembly. Assembly cannot work as fast as the machining tool with this batch size. And this is the important part for our course, the inventory of this machining step will start to build up. A little buffer in there. These bases and propeller heads will start filling up in our system. They're not able to be processed quickly enough. So here we see one of our wastes. What can we do? Well, here we are with our batch size of 10 and this 9.68 units per hour. Let's look at the capacity of the assembly. Now we already know it's 9. There's no batching there. You assemble at, 9.667 minutes per unit. It gives us 9 units per hour capacity. And this, as we already actually calculated, corresponded to a batch size of 3 in our machining. We can check that. This time, look, we're assigning the capacity assembly of 9 units per hour, which is 0.150 units per minute. And if you would rearrange this equation and solve for the batch size, you'd end up finding out that a batch size of 3 will give you the same values. So what this means then is that if we choose a batch size of 3 instead of 10 for our machining, so here batch size of 3, we will have 9 units per hour at the machining as well as 9 units per hour at the assembly. And so we have our system aligned. We have no buildup of additional parts. Now again, this is an ideal case. We haven't been talking about variability, and we haven't been talking about our takt time. So let's look at this a little more closely. If we look at a classic example from the automobile industry, where you have, this is my very bad picture, but you have large sheets of steel that are then moved into a stamping press. in order to form the different parts of the car. For example, the hood of the car, or the sides of the car, the doors. And of course, this depends on what kind of model you have. So if you want to produce different models of car on the same line, you would have to change these dies that are used in the stamping press. And the way this works is that you have the shape, the form that you want in an upper and a lower die, which are then pushed together over the metal to form the part that you want. And here we see some pictures, and you can read a little bit more about it here in this website. Now, we're going back a little bit in time. We're looking at the early American automobile production. This, of course, is the classic example which led to many of the ideas then that in Toyota that led to the lean production. These dies used in the stamping press were very, very heavy, and they had to be perfectly aligned. And this required, at the time, a full day to change the dies. And this was performed by workers who specialized in the die changing. And so one production line could produce different models of car, but every time you needed to change models, you had to change the dies, which took a very long time, very long setup time. So given this, the batch sizes for models were kept very large. So I'm just going to sketch this. We don't have to calculate anything. We just need to understand the idea. So here we have time, right? Very long time. And here we have our inventory. So what we do is we put our set of dies in, and we start stamping out car parts for model type A, for example. And if you bring this to a general example with large setup times, you have a certain product, for example. Well, model A is produced and for a long period of time, and then once that period of time is over, you can start producing the parts for model type B. You can go on to model type C. We go back to your model A. Either way, our line is able to produce, in this case, two different types of parts, but because of these long setup times, we're choosing very large batches, and we're building up a large amount of inventory. Now, we had the example with the propeller, where then our assembly process was then moving those parts out at the same rate. However, we've talked about takt time. Now, takt time is the regular drum of the customer demand. Now, do you think our customers only want to take model A and then suddenly only want to take model B? Probably not. Probably they want some of model A and some of model B, sort of all in the regular time. So this means if you've adjusted your assembly line for the parts that are not with this setup to the customer demand, that means you're going to be taking some of model A, and then some of model B, and then some of model A. So this inventory will get sort of gradually used up over time. And the model B will gradually get used up, and so forth, and so forth, and so forth. So if you're following then the customer demand, you can expect when you have large batches to have large inventory in your system. Now, if you decide that you can use a smaller batch, you produce model A, and then you produce model B, and then you produce model A, and then model B, and this will still get used up, at possibly a slower rate there, but your average inventory, maybe I should change my color here, your average inventory for your car parts here is going to be much higher than the average inventory, much higher in the, this is with a large batch. This is a small batch. Much higher when you have a large batch. And of course, as we've been talking about, the inventory is one of our wastes. And we'll see also that in a later section. The significance here is that setups are often necessary to add flexibility to the production, because different products may require setups between different product types. And batching products of a single type into large batches is going to minimize the effect of the setup times on the resource capacity. And we looked at that with our windmill example, with our propeller example. However, this batching comes at the expense of inventory in the process. We see a trade-off between maintaining our resource capacity and minimizing inventory in the presence of setups.